Hi students, we have come to the last video of colligative property. This is our last colligative property which we are going to discuss, and that is osmotic pressure. We understand the word pressure, but what does that osmotic means? So it comes from the pressure due to osmosis. Of course, that will not help, right? What is this osmosis then? So osmosis is a fancy looking word, but if you can understand diffusion, it is just a opposite of that. Think like that, build that intuition like that. Opposite of diffusion. And now if you don't understand diffusion, don't worry. I have two things for you, one perfume bottle and one water beaker having water. Okay. So when we spray the perfume, what happens? So these perfume particles will go like this, right? And you can smell the perfume around the room. That's what happened. Simple. So this process is called a diffusion. Why? If you see the molecules, perfume molecules, they are moving from here, let's say this area, if I ask, to here, right? If this volume, if I ask how many perfume particles are there, you will say less. Here, very near to the perfume bottle, the concentration of perfume will be more, right? So the particles are moving from, this is the low concentration, right? Low concentration, and this is the higher concentration of perfume particles. So the particles are moving from higher concentration areas to lower concentration areas. And this process is called diffusion. Okay. Similar when we mix sugar with water. So sugar will not stay here like that, right? It will go into the all parts where the less concentration of sugar is. It will spread out, it will disperse. This is again diffusion. So you can see it in our common daily life, like perfume diffusion is there and water also. So the sugar went from very high concentration, area to the lower concentration areas or volumes. So this process is called diffusion. Now, what if I ask you, can we do opposite of that? What does that mean? I mean that the particles will move from low concentration area to higher concentration areas. Can we do that? Think about it. What I'm saying is, like if there is a like water here, and if I'm talking about the opposite process, so what should happen? That our higher concentration area should be there, but water should reach here. Water should go from lower concentration of sugar, they should go to the higher concentration. So I'm talking about the reverse, or I'm talking about the opposite of diffusion. And that is what the osmosis is. It is the movement of particles from low concentration to higher concentration. So now create some pressure of osmosis. Let's do some osmosis. For diffusion, I have used perfume, this water and sugar. So what is my setup? Let me show you my setup for osmosis. So this is my setup. Okay, first understand what I have done here. So here I have two compartments of these beakers. Okay, so one of the right side one have water plus sugar. So it's a solution where you can say sugar concentration is more, right? Concentration is more of sugar. And on the left side, it is a lighter area. I wanted to show the concentration is less. Actually, this is just water. You can say sugar concentration is zero, but we can just say that concentration is less. So here I have water, a solvent, and here I have a solution. So the concentration of solute particles is more here. Here it is like negligible, right? Very low concentration. And now I'm going to do osmosis. What I will do, I will open this gate. Do you think that will happen? No. In that case, diffusion will happen. These particles, which are at higher concentration, they will move into the lower concentration area. I want to do osmosis. And for that, I have a special kind of separation. And this separation will have small holes in it. Okay, small holes in it. We also call them a fancy name, pores. Right. So there, are you able to see? Let me draw bigger ones. Yeah, so these will be having small pores, kind of a membrane. We have a name for that. We call it semi-permeable membrane. Okay, so this semi-permeable membrane or the separation is what I will keep it here. Okay, I will not open it completely. I will open it with this membrane which has tiny, tiny holes. And after some time, you will see this water will start pushing, creating some pressure here on these holes, entering into this, higher concentration areas. And here what you are seeing is the osmosis. So you will see this compartment's level of, volume of liquid will rise because water is entering from here, right? And now there will be one question which I want to clear here. You'll be seeing that if there is a small hole, why these particles, sugar is not getting that side? If you want to compare the size of the water molecule and the sugar molecule. This will be the real life example. So if water molecule is the size of a marble, sugar is a big molecule of a soccer ball. So that's why having this tiny pores, okay, tiny pores will only allow the water molecules to enter because they are tiny in size. But these big sugar molecules, they cannot pass this membrane. That's why this membrane is necessary for the osmosis process. So this is the osmosis process. Here we have higher concentration of solute particles, and here we have low. It is only solvent here. And we see that, the solvent, the solvent apply pressure here. For osmosis, it tries to enter here. But now think about a moment. What if I want to stop this process? So I need to apply the same pressure which this process osmosis is applying. So what I will do is I will apply this side some pressure, and the pressure which I'll apply, if it prevents these molecules, water molecules, to enter this medium, I can say I have created the pressure, or I am applying the pressure which is equal to this osmotic pressure, and that is what the pressure is called, osmotic pressure. The pressure which prevents osmosis, that pressure is called the osmotic pressure. So let us summarize here. What is osmotic pressure? It is the pressure applied to the solution, right? This was a solution, right? Water plus sugar. So pressure applied to the solution to prevent passage or movement of solvent, which was water in our case, into the solution. Now let's do the formula part of it. The osmotic pressure is denoted by P in some textbook, or pi. So I'll be denoting it by pi, and it is equal to CRT. So what are different things? This T is of course a temperature. This R is gas constant, and this C is nothing but concentration. And concentration, if you are confusing like what is the concentration, it is just a number of moles of solute particles in per unit volume. So whatever the volume we have, number of moles, if you divide it, you will get the concentration number. We denoted by letter C. And if you want to plug this in, like if you want to say this is, let's say, N number of moles and this is V, you can modify this formula also. So you can say pi is equal to N by V RT. So that way also you can remember this formula. So again, see the colligative property, the osmotic pressure, the pressure we need to apply on the solution so that osmosis does not happen. The solvent particle does not enter into the solution. It is also directly proportional to the concentration, right? This part is concentration. This is constant, and also we are doing experiment at, at a constant temperature. So this, both things are, are a constant. So we can say that pi is directly proportional to the concentration, and that is why it is called osmotic pressure. Is we are calling that a colligative property, which depends on the number of solute particles.